Hi, today I want to talk about the sidecar approach for securing microservices, and we will assume JWT authentication. We can view a sidecar as a companion application that can either live in the same process as your microservice or be deployed within the same unit. The sidecar in this case would be some kind of helper application that would coexist with your microservice, and we assume that if there is a difference in terms of networking, the latency is very low. The goal of this presentation is to show developers a different perspective for securing and protecting microservices, and I will use Java for a sample project to demonstrate it. Let's take a look at the documentation of the sample application. The first thing that I want to note is that the code is incomplete on purpose. I created this sample application for integration with a Kubernetes cluster, but there are no strong dependencies against Kubernetes. This approach used a lightweight proxy using a Java library in comparison to a Netflix Zool or similar products. Why did I create this application? When developers are asked to secure microservices, the first thing that they might try to do is to code the security layer directly within the application. Another approach would be to have some kind of central access. In the case of the Kubernetes cluster, we might use an ingress endpoint. But most of the time, we have an existing security service that is central for all our microservices. The approach that I'm proposing uses a companion helper, a sidecar, which is deployed along our microservice. So how can we benefit from a sidecar approach? In contrast to a central proxy, we don't have to worry about scalability or the concept of global liability. Each microservice will have its own dedicated security service. This security service is pretty light. It doesn't use any fancy framework, and it only contains basic abstractions in the code base. The overall configuration is simplified because we don't need to worry about caching, especially when we have a central security service that needs to take care of managing public and private endpoints. Let's take a look at the architecture of our sample project. Again, I want to remind you that the code is incomplete, so please don't use it in a production system. Looking at our deployment diagram, on the left side we have a client application. Typically that would be a web application. We assume that that web application is authenticating the user against an identity provider in order to get a JWT token. Once the client has a JWT token, it will interact with our backend microservice in yellow background, and the JWT token will be placed inside the HTTP headers. It will go through Kubernetes in this diagram. First, it will hit the ingress endpoint, and usually you will have what is called an ingress controller, Nginx, HA proxy, or similar products. Once the request hits an ingress, it will get through a Kubernetes service, which is pretty much an internal router most of the time. And that service is connected to our authentication sidecar, which acts as a proxy to our microservice. Our security flow is quite simple. Once the user request hits our sidecar, we will check whether or not the URI is public or protected. Most security services that I've seen so far use a set of regular expressions for public URLs. In some rare occasions, I've seen security services try to cache the full list of public URIs. That is pretty uncommon. Once we know whether or not the requested URI is public or not, if it's public, we will just forward the request to our backend microservice. Otherwise, we extract the token from HTTP headers. We verify the token signature as well as the JWT claims. We extract the user data, and we inject some additional HTTP headers that will be forwarded to our microservice. So our microservice will not have to parse again the JWT token in order to get the user data. This project relies on a minimal set of dependencies. We use Jetty as application server, have a library for parsing JWT tokens, and a proxy servlet component. The user request will go through our authentication filter, which is a plain servlet filter. That servlet filter will ask the public URIs container whether or not your request can go through without authentication. Assuming that the URI is protected, we will relay it to our authentication service that will grab the JWT token from HTTP headers, verify the token, extract the user data prior forwarding to our proxy microservice. The main components of our application would be the servlet filter that will have a handle on the public URIs component as well as our authentication service. That authentication filter will be able to export user information at some point. So we hit our authentication filter. We check the requested URI against our public URIs container. We ask the authentication service to extract the token from HTTP headers, and we import the user data from JWT claims in order to populate a user data object. That user data object is later on exported and injected within HTTP request headers prior forwarding the request to our proxy microservice. Let's look at the sample code. We have a Maven project, and the POM is pretty minimal. At the top you have the typical Maven data and a set of Maven properties for artifact and plugins versions. Our main proxy component is here. It's just a plain servlet. We use Jetty as application server and some other libraries for JWT parsing or for testing. For this project, I'm using JMockit. I don't quite like Mockito, especially when it's combined with PowerMock. People who have used Mockito in the past probably recall some annoyances in terms of dealing with libraries conflicts and some cryptic errors. With JMockit, you have a clean and consistent API. You don't need to use an external library in order to mock static methods and things like that. We modify the final name of our jar artifact in order to exclude the project version, and we employ the Maven assembly plugin in order to create a file jar with all the dependencies included. So this is similar to having a file jar with Spring Boot or similar frameworks. Let's take a look at the entry point of our application. So what we do, we get the server information from environment variables, as well as the public URIs of our backend microservice, and some parameters that will be used by our JWT authentication service. In this case, we have the JWKS URL. Typically, the JWKS URL is a JSON endpoint where you can access public keys required in order to verify the signature of a JWT token. Prior starting our JWT server, we will add our authentication filter and our proxy servlet. The proxy servlet is a third-party library configured here. We don't do anything special. And in fact, the only thing that we do is just specify the URI of our proxy microservice in order to forward the request. Our custom component is the authentication filter that takes as init parameters some public URLs in terms of regular expressions and a JWKS URL for JWT authentication. We initialize our filter, and what we really care about is being able to construct a public URIs component as well as our JWT authentication service. Our public URIs will be comma delimited from the filter's configuration derived from environment variables. That authentication filter extends a class called oncePerRequestFilter, which is not a Spring component, and I will get to it later. Once the user request hits our authentication filter, the first thing that we do is set the user to anonymous. And we wrap the incoming HTTP servlet request in order to be able to modify HTTP headers down the stretch. If the requested URI is protected, we try to authenticate the user via JWT tokens extracted from HTTP headers. So that will come from our JWT HTTP headers token source. The JWT HTTP headers token source component looks for the value of the authorization header and more specifically a bearer token. And it just implements the Java supplier interface in order to return the JWT token string in base 64 without any kind of modification or transformation. If you look at the business logic of our service, we see that there is nothing special, lots of to-do items. In the real world, what we would do is try to get a set of public keys used for signing the JWT token. We will use the public keys in order to verify the token signature. And we also may want to validate some claims within the JWT token. In this case, I'm not really doing anything. I'm just constructing manually a set of claims and returning that. So once we try to authenticate, we first extract the claims. We don't do any validation and anything like that for now. And from those claims, we will try to create some Java component that will be used to construct a user object. Once we have our user data within our user importer, we can create a user object from it. And assuming that we had no exceptions during the authentication, we will take the user information and inject it inside some HTTP headers. Given that we have a servlet request wrapper, we will be able to customize HTTP headers, which by default are immutables. When the authentication fails, we return a status code 401 for unauthorized requests. Let's go back to our user object. And we see that we don't have any getters and setters. We can only import data via a user importer or export data using a user exporter interface. And let's open those files. Here we have the user exporter, and in this case we have our user importer. Our once per request filter is similar, I think, to the Spring framework implementation. You want to ensure that the business logic of the filter is only evaluated once, regardless of how many times our filter is invoked within the same request. And we managed to do that by using HTTP servlet request attributes and setting a flag. There are a couple of unit tests, and the first thing that I did was to create a set of utilities in order to deal with servlet API abstractions. So I want to be able to partially mock some servlet API components such as the request, the response, the filter chain, or the filter configuration. So this is plain Java, nothing really special. Just want to be able to invoke just the minimal subset of methods that I need in order to run tests. This is our public URIs component test class, which is parameterized. And we will just assume for simplicity that we have a set of regular expressions, A, B, C, and B, C, D. And those would be our public URIs. /ABC would be our requested URI. And the last parameter, Boolean flag, would be the expected value, whether or not we expect the requested URI to be public. In our authentication filter, we don't do much. We ensure that our authentication service is mocked. In any case, it doesn't really contain any business logic associated to validating a JWT token. So this is left to the discretion of the implementer for further enhancements. So let's try and see whether or not those tests run. Okay, it looks like I forgot to make a change. So let's take a quick look. I renamed the variable rec to requests in order to be more explicit. Let's try to run it again. And we see that all our tests are able to run successfully. So when we go back to our architecture documentation, what we wanted to do was to use a sidecar approach in order to secure a backend microservice, possibly deployed on Kubernetes. And we are using this approach in case you might not have the luxury of using a fully blown service mesh such as Istio. I played around with Istio early this year, and I think that it's not ready for prime time yet. What I would like from Istio is more flexibility in terms of customization without having to write some Golang code. I'm a Java developer, and ideally I want to be able to integrate my own components using Java code and just registering some functionality via gRPC or REST or any kind of protocol. At this point, Istio is promising, but I think that I would only use it on an environment where I have more or less full control over the infrastructure. So for example, if I'm deploying my applications in the cloud, there might be a set of features required by Istio that I'm not able to guarantee. And again, when we look at a possible approach, we could have used the central proxy. So for example, we could have had an authentication service just between the client and the entire cluster, which is Kubernetes in this case. And that would have introduced some kind of global liability and potentially some configuration and scalability concerns. What we chose to do instead is to deploy our authentication component within the same deployment unit as our backend microservice. That means that for each microservice deployment, we will have a dedicated authentication service. And the developers implementing all those microservices for your company or your business don't really need to worry about the details surrounding that sidecar container. The only thing that they need to be aware of is that someone will inject the user data from HTTP headers. And as long as those HTTP headers are present, it means that the request had been previously authenticated. And because the sidecar and the microservice reside on the same deployment unit, we can assume that this is secure enough, in my opinion. Because even though we could break the security of one given microservice, you still have to do pretty much the same thing for every single microservice, which may or may not be that difficult, but at least you don't expose the entire cluster at once if there is an intruder. Thank you for your time. I hope that you found this presentation useful. Bye-bye.